Okay, everybody, so I'm going to tell you a really funny story. So at about 4 o'clock, I recorded this, and I had everything good to go, and then it turned out that none of the audio had been working at all. So it is a little bit after 5 o'clock. I've skipped yoga for this. I'm going to go ahead and I'm going to try to re-record this, and we're going to see what happens. So the last time that we were here, we were talking about our good old friend depth perception. So depth perception is going to be really critical because this is what helps us judge distance. This is also what allows us to better locate objects, to understand where they are in relationship to us, and thus allow us to act on the world. So depth perception is actually, when you really think about it, pretty cool. Just to kind of put this into perspective, your retina is a two-dimensional space. And so what we are basically doing is we're taking a three-dimensional world, turning it into a two-dimensional space on our retina, and then from that image constructing our three-dimensional perception of the world. Additionally, our geometry changes from outside world to retina to our representation in the brain. We live in a world of Euclidean geometry. So when we look at triangles out in the world is composed of lines, parallel lines, and when we add up the angles of a triangle, they always equal 180. When you go and you take that image and put it on the curved surface of a retina, the geometry then becomes non-Euclidean. And so from that, we actually shift to a non-Euclidean space. You add up the angles inside a triangle, they are suddenly going to be greater than or equal to 180 because of that curvature. And we can use multiple cues to actually help us out. So let's talk about some of the different ways that we actually use cues to help us figure out the world. So we have what are called monocular depth cues. These are cues that you only need a good working single eyeball to work with. So you can judge depth and distance only by using a single eye. And we're going to go through examples of each of these in greater detail. Linear perspective, texture gradient, which is different from texture segmentation to find boundaries, shading, interposition, and familiar size. So linear perspective is actually pretty straightforward. It's the idea that the world is made up of parallel lines that appear to converge in the distance. And so what you can kind of see in this picture is that these lines are kind of operating in parallel, and additionally, the farther away in the distance that you are, the more closely they appear to converge. We also have a texture gradient. So here in this picture of bunnies, the bunnies that are larger and closer to you, you can see more detail in their fur. You might even be able to see their whiskers. If we focus on the smaller bunnies farther away in the back, we have less detail. We see less of their fur. We do not see whiskers. So as we get farther away from something, the texture becomes less detailed and less noticeable. Shading is pretty straightforward. We can use light to highlight areas that we want to pop out. We can use shading or darker colors or contours to create areas that are concave, areas that go inward, to create some additional depth and distance. And then we have interposition. As a general rule, objects that are closer to us block objects that are farther away. So in this image, you can see that the circle is the closest to us because none of it is blocked. It does block the square, which in turn blocks the triangle, which helps us figure out that the triangle is the farthest thing away. We also have familiar size. So as this is actually making use of our experience with objects and our knowledge and our top-down processing. So when my hand moves further towards the screen, it becomes larger on your retina. Now, is my hand suddenly growing? No. You know what the size of a hand is, so you know that hands don't suddenly shrink or grow. If it's becoming larger on your retina, as it is right now, that means that it's moving closer to you. If it's shrinking, again, hands don't just suddenly grow and shrink out of nowhere. You can determine that your hand has moved farther away. So we use our knowledge and our understanding of objects that we've experienced before to help us judge depth and distance based on how large or how small they are on our retina. Now, those are the monocular cues. Binocular cues basically use both eyes. So each eye occupies a slightly different view because they are occupied in slightly different places in your head. So this is what is known as binocular disparity. Each of your eyes is looking at a slightly different thing. And we use the differences between our eyes to help calculate depth. Being able to do this is what is known as stereopsis or stereo vision. So if you want to test this out, you can do what this person is doing. Hold one finger very far out, hold another finger closer to you, and take turns opening and closing each of your eyes. What you should see is that the finger that is closest to you will appear to jump over the finger that is farther away. The finger that is farther away doesn't really move at all. And that's because the closer that something is to you, the more different each eye's view of that finger is going to become. When it's far away, they're not that different, but when they're up close, each eye is getting something very, very different. We can use this information to help us figure out depth and distance. And we have things like stereograms, so 3D movies help capitalize on this information. So do stereograms or stereoscopic images like this. This is a magic eye picture. If you let your eyes relax, you should be able to see a spiral. If you're like me and you can't do it without crossing your eyes, this is one that is specifically developed for cross-eyed people. As you can kind of see here, it creates that same spiral. In addition to our monocular cues and our binocular cues, our ocular motor cues actually use our physical eye movements. So we have vergence, where our eyes will either move inward or outward to focus on an object. And we have accommodation. So our lens will actually thicken to help boost our focus on objects that are closer to us. Okay. So now we've talked about visual perception and being able to figure out object features to help us recognize objects. Now we're going to move on to talking about subliminal perception, which I think you will find pretty fun, and also talking about pattern recognition, object recognition, and face recognition. So here's what we're going to cover, and y'all, we're going to finish all of it, I promise. This is going to be a little longer lecture. It's going to be about 48 to 50 minutes. Right now we're coming on 8 minutes, so if you feel like you need to take a break and pause the Dr. G time, you are welcome to do that. So we're going to cover subliminal perception. We're going to talk about different theories of pattern recognition. We'll talk about different theories related to object recognition. And then we'll finish up by talking about face recognition and whether or not faces are special. If you watch all of this, by the time that we get on Friday, we can talk about not facial recognition, we're talking about that now. We'll talk about visual attention, and we will also talk about objects in action, and I will throw little plushies like Mr. Neuron at you. Okay, so subliminal perception, is it actually real? So oftentimes you will hear about subliminal perception, the idea that you can slip a message to people that they are not aware of consciously, and it will somehow alter behavior. And so one of the things that often gets brought up, I first heard about things like subliminal advertising and subliminal perception by watching an episode of Saved by the Bell. Odds are pretty good that you have had some exposure to this concept as well. But what a lot of different TV shows and media often forward is a very famous study by Vickery in 1957. The urban legend basically is that if you flash things like eat popcorn or drink Coca-Cola without people consciously seeing them, sales of both will go up. James Vickery supposedly did this at a theater in New Jersey during a showing of Picnic. Now, that's all well and good, but it turns out this entire study is a hoax. And despite all of this, you have probably heard this story somewhere on TV before. So what does it mean for perception to be truly subliminal? So Miracle back in 2001, along with colleagues, basically said that when you're talking about something that you are consciously aware of, you actually have two different thresholds. So first of all, you have your subjective threshold, and that's whether or not you report a conscious stimulus. I saw this thing. I saw this, it said eat popcorn. I saw this, it said drink Coca-Cola. So that's your subjective threshold, whether you personally see it. We also have an objective threshold. Has this been presented quickly enough that you could not perceive it even if you wanted to? And that's more objective. It's based on how quickly something shows up or how quickly the words eat popcorn or drink Coca-Cola appear on the screen. So one of those is based on your report. One of those is based on would you be able to even see a flash or perceive it? For something to truly be subliminal, Miracle and colleagues actually reported that something has to be below the objective threshold. So it's not even whether or not you would see it, it's was it presented so quickly that you wouldn't even perceive it. So despite the fact that it's subliminal, it still has to alter behavior in some sort of way. So there is some evidence that this is actually real. This comes by Nakache and colleagues in 2002. And they did a pretty simple task. They gave people digits, so they gave people numbers, and they said, is this number greater than 5 or less than 5? Pretty straightforward. However, they added a wrinkle to this study that made it a bit more complicated. Just prior to presenting a consciously perceived digit, they gave a subliminal prime, which was a digit. So this digit was also either greater than or less than 5. So here's what's really interesting. The target is either greater than or less than 5, and so is the subliminal prime. So this means that you could have one of two outcomes. You could have a congruency where the prime is something like 2, and the target is something like 4. Both of those are less than 5. The response to both would be the same. On the other hand, we could have something that's incongruent. I give you, my subliminal prime is the number 7 that I show before I show you the number 3. One of those is greater than 5. The subliminal prime is greater than 5, but the actual target is less than 5. Those responses conflict. So if the subliminal prime has an effect, it will make more of a difference when the prime is incongruent with the target, and that's exactly what Nakache and colleagues found. People made longer responses when the prime and the target had incongruent responses. However, both of these findings are really hard to replicate, and they're very highly contested. So whether or not subliminal perception is real, it's debatable, but that doesn't stop advertisers from trying to put hidden messages in their work. Now, I would argue that none of these are truly subliminal. You can see these two people having a tortilla chip over a bowl of salsa. That is not subliminal. If it's presented to you long enough, and if you looked for it hard enough, you would see it. For something to truly be subliminal, you would not be able to perceive it at all. So now we're going to move on to something that's not as fun as subliminal perception. We're going to go ahead and talk about pattern recognition. So how do we understand object recognition? So we've taken an object, we've separated it from its background by focusing on the edges. We're starting to look at its features by processing color and depth. Now we have a two-dimensional pattern. So when people have done research with pattern recognition, they have often done this with letters because letters are pretty straightforward, they're two-dimensional, and they're very well known. So some of the earliest theories of pattern recognition was something called template theory. The basic idea behind template theory is that for every possible visual pattern that you encounter out in the world, you have a template stored up for every single one of them. So for each object visually that you encounter in the world, you have a template for it. And when you are finding something and you're trying to recognize what type of object it is, you search for all of the templates that are available in your mind, and the one that is the closest matching one wins, and that's what you identify it as. So there's kind of a problem with this, though. The idea that you have a template for every possible visual thing that you encounter. And remember that most of this is being done with letters. All of these are the letter A, and you probably recognize them all as the letter A really quickly. Our visual system is really flexible. You know that these are A's despite differences in orientation, differences in font, differences in size. However, the template theory basically says for you to notice that all of these are A, you would have to have every single instance of that template stored. Each of these would be a template stored in your mind. And in this case, that doesn't really make a lot of sense. That's a lot of different things you have to search through. And that's not even including the fact that you may know more than English letters. You might know other languages. And in that case, you would need templates for those as well. So that's a lot of stuff to search through when our identification of these patterns is very, very rapid. So the next idea that comes up are feature theories, and these are going to be a lot more flexible than those older template theories. So when we look at these A's, we're not searching through a template. We notice that all of these are A because they share some features in common. They are made up of two diagonal lines with a horizontal crossbar. And basically, any pattern that you encounter in the world has a set of features or attributes. You recognize a pattern because it fits the features for a particular item. And focusing on features rather than the exact visual pattern permits flexibility in a way that template theory really doesn't have. One of the other major assumptions of feature theories is that we're going to focus on the smaller details, local features, before we focus on what the pattern looks like overall and do global processing. So what evidence do we have for feature theories? So I'm going to keep this pretty simple. We're going to try this, and don't raise your hand, but I'd like you to identify when you find the letter Z in each of these lists. So here's list number 1. Okay, were you able to find it? Here's list number 2. Odds are pretty good. You had an easier time finding the Z here than the Z here. And if you take a look at the other items in these lists, I think you can see why. List 2 is going to be easier because notice that none of these other distractors have features in common with Z. Now compare that to list number 1, where quite a few of the distractors do share some features in common. Ulrich-Neisser found that our search is going to be the fastest when our target shares fewer features with the list. However, I did mention that feature theories really support the idea that we process local features over global features. But there is some evidence that depending on the situation, we process the global image first. So Navin presented people with figures like these and asked them to identify either the local feature or the global letter that this made. So here we have a global H made up of local features of smaller S's. And what's interesting is that Navin found that we actually process global features first. And he found that local features are often going to be harder to identify when they're incongruent. It's harder to identify these S's when it doesn't match with the global feature. On the other hand, if this H were made up of H's, so we had a congruency, it'd be easier to notice the smaller H's. So what's interesting is that us being able to identify the smaller features depends on whether or not they're congruent with the bigger letter. On the other hand, identifying the bigger letter doesn't seem to depend on congruency. We identify it equally well whether the local features match that global shape or not. And it's been suggested that attention might play a role. So what you're looking at here are stimuli from Dalrymple and colleagues back in 2009. Global processing does seem to require attention because it was harder for people to do when the local features, the letters that made up the bigger letter, when they were larger, as you see here, and when they were more spread out. It actually becomes harder to identify the global letter based on that. So whether we process local features or global features ultimately depends on the circumstances around us. Now, your book talks about feature detectors in the brain. If you're using the second edition of the book, it'll be on pages 37 to 38. If you are using the third edition of the book, it'll be on page 46. You can go ahead and read about those in your textbook. So I want to talk a little bit about the role that top-down processes play. So a lot of these theories of pattern recognition that I've been talking about, including feature theories, are all based on bottom-up processing. We start with the stimuli that we are given and we work our way up to more complex processes. But our expectations and our knowledge of the world around us is going to play a role. Top-down processes help us out too. So we're going to try an example here. I'm going to flash you a bunch of letters on the screen, and I want you to see if you can identify them. Did you see a letter E in that string that I flashed? Now we're going to try another one. Did you see the letter R in that one? So I'm going to close out of this really quick. So what you can see is that I briefly flashed you the word makeshift. This is an actual word. On the other hand, I gave you a random string of letters that don't make any kind of word. It's probably going to be easier for you to find that letter E when it's part of a word. It's harder for you to identify a letter when it is not part of a word. So this is a case where top-down processing ultimately helps us. We get what is called the word superiority effect. It is easier for us to identify a letter when it appears in a word. Top-down processing helps us process those local features much more easily. So just something you should know. Okay, so now we're going to move on to object recognition. So one of the major problems with object recognition is that objects vary in their features. All of these are chairs, but they all look really different from each other. So the question becomes, how do we know that these are chairs? All of them have in common that they have a horizontal surface that you put your rear end on. But some of them vary in back support, some of them have no back support, some of them have arms, some of them don't. So let's talk a little bit about some of the theories about how we recognize objects. So why is object recognition so important? And why are we talking about it here? So we're talking about it here because one of the goals of cognition is to act upon objects that are in the world. And you need to be able to recognize an object and its features to be able to act upon it. So we're going to talk about two different theories of object recognition that were developed in the 80s, and they've been incredibly influential towards our understanding. We have Marr's computational model, which was developed in 1982, and we have the recognition by components model that was developed by Biederman. So we're going to start with Marr's computational model. Now this is a computer model. We're not really going to talk about the major details of computers and computer modeling in this aspect. We're just going to focus on the basic ideas of the framework. So object recognition, according to Marr, happens in stages, and each of those representations that we form is increasingly complex and uses a different type of information. So the first thing that we're going to do, according to this model, to help recognize objects is create a primal sketch. This is a two-dimensional description of the major light intensity changes. So it's going to look at things like edges, things like contours, blobs of light or shadow. From that primal sketch, we're going to develop what's called a 2.5D sketch. So we're going to focus on the depth and the orientation of surfaces. And that's going to include focusing on things like shading, like texture, and motion, if it's present. And then finally, we get what we call our 3D model representation, where we actually get the three-dimensional object out in the world, and at that point, we're able to recognize it. So one thing I will mention that Marr is very much about is that this is viewpoint-invariant. What this means is that you should be able to recognize the object easily regardless of the way in which you are viewing it. So the viewing angle does not matter for recognition. So here's what this looks like. So we have our primal sketch right here. We have our 2.5D sketch. And then we finish with our 3D model representation. So why is this model so important? It was the first to really acknowledge how complex object recognition really is. It's something that you and I take for granted every day. Additionally, this is a very well-known comprehensive computational framework that inspired a lot of other models, including Biedermann's model. And then one of the other major things that we'll come back to is it's one of the first models to create debate on whether or not viewing angle matters for recognition. So Marr believes that it's viewpoint invariant. You should be able to recognize something equally well regardless of viewing angle. Other people have said that viewpoint matters, and some viewpoints it's easier to recognize objects than others. So now let's move into Biedermann's recognition by components theory. So this was designed to be an extension of Marr's framework. And one of the major assumptions that Biedermann has is that all objects in the world are made up of 36 basic shapes. And you can use those 36 basic shapes to create any object on Earth. And he called these geometric icons or geons. So you can see a couple of them here. We have a cylinder, we have a cone, a pyramid, a football, a horn, and a wine glass. Okay, a wine glass. And so the idea being that you can take different geons, so here are a few examples, and you can make a variety of different objects from those geons. And the idea is, if you want to recognize an object, you first have to break it down into its geons to be able to do that. So what are the key steps of the theory? So some of these things you might need to know, some of those things you probably will not need to know, and I will tell you which is which. So the first thing that we need to do is we need to extract the edges. So we need to figure out where the edges of the object are, separate it from its background, much like we would do with any object. From there, we're going to parse areas of concavity. As it turns out, areas that are concave, that bend inward, help us recognize an object more easily than when they are not included. We will also focus on the invariant properties of the object, which I am not going to test you on. That will include whether or not there are points on a curve or in parallel, cotermination, so when two edges start or end together, symmetry, collinearity, so things basically falling on the same line. So we look at concavity, we focus on the invariant properties, and from that we determine the geons that are involved. From that, we can match to a representation and identify the object. Now, what evidence do we have for processing concavity to help us recognize objects? So I want to focus in particular on this watering can. So you can kind of see here that when we don't get rid of areas that are concave, it's actually really easy for us to find the watering can. Once I take out the regions that are concave, it is a lot harder for us to do. And you can actually see that's also true for the stool, the scissors, the wine glass, and also the cup. Leake and colleagues back in 2012 also found that when you're looking at pictures of objects, people tend to move their eyes towards areas that are concave. Again, suggesting that for us to be able to recognize an object, we tend to focus on areas that are concave and move inward rather than those that are convex and pop outward. Now, I want to get back to this notion of viewpoint invariance because this came up in Marr's model and it comes up in Biedermann's model. And viewpoint invariance is the notion that an object can be easily recognized from all viewing angles. So viewing angle does not matter. But for those who believe that this is the case, I want to show you this. Can you tell me what that is? You probably wouldn't be able to tell very easily from this angle. On the other hand, if I show it to you from the side, it's probably a lot easier to see that it's a bike. So viewpoint invariance, I just gave you an anecdotal case, but you can see that viewpoint clearly matters for object identification at times. So a lot of people have found that viewpoint only matters in certain types of situations. So if I'm trying to tell the difference between a bike and a car, I don't need to worry about viewpoint there. There's enough differences between these two categories that I can clearly tell the difference and viewpoint won't matter. And Tarr and Bolthoff actually found this out in 1995. However, for harder discriminations that are within the same category, you might need a better viewing angle. So viewpoint dependence might be necessary for harder discriminations like these. Here we've got two different cars, two different makes and models, but they look similar enough that we're going to need to look at them from a different viewpoint to be able to determine that this in fact is a PT Cruiser and this in fact is a Fiat. What is some additional evidence to support that sometimes viewpoint matters? That it's not always invariant. Gauthier and Tarr back in 1997 presented people with these three-dimensional objects called greebles. So they saw pictures of these objects, and you can see that every single one of them looks really different from each other. And what they found is that when the task was really easy, participants got feedback and the discriminations weren't very detailed, they weren't very hard. Viewpoint invariance tended to be the thing. So viewpoint doesn't matter when the discriminations are easy and the task isn't hard. But we do find that when the task becomes harder, that viewpoint dependence matters. And you can kind of see that in these particular cases, a lot of these are similar enough to each other that viewpoint might matter a lot more. So now I want to talk about what happens when brain damage prevents you from recognizing objects on sites. We're going to talk about agnosia, when object recognition fails. So this will often happen due to damage to the inferior temporal cortex. Visual agnosia is the inability to recognize objects by sight, but other senses can be used to help, including touch and hearing. So it's kind of clear that the inferotemporal or the inferior temporal cortex is critical. And this is where object knowledge and memories of interacting with objects are stored. So my question to you is, what visual stream is this? We've talked about the dorsal pathway for where objects are located. We've also talked about the ventral pathway, which helps us recognize what objects are. So what visual stream is this? The inferior temporal cortex is a part of that ventral stream, that what pathway. So patients with agnosia have generally helped us to better understand object recognition. And historically, there have been two different types. We have apperceptive agnosia, so these are people that literally have problems with impairments in perception. Apperceptive literally translates to without perception. Then we have people with associative agnosia. These are people who have impairments in accessing object knowledge. So historically, people have distinguished between the two by having them copy figures. Patients with associative agnosia generally can copy images because it's object knowledge that is the problem, not perception. People with apperceptive agnosia generally cannot. So here are some examples. So here's apperceptive agnosia. You can see that there's clearly some problems with perceptual processing. And then we have associative agnosia. These people can copy things, but they won't be able to tell you what they copied. So here's the problem though. From a historical perspective, it seems really easy to understand, but it's going to be a lot more complex than that. Figure copying tests are not going to be subtle enough to capture some of the deficits that we see in different types of agnosias. And there are historically complexities even within the same type of agnosia. So Riddick and colleagues talked about two patients with apperceptive agnosia, and the two of these patients had very specific and different problems. SA, one of the patients, had difficulty grouping edges together to help understand object form and shape. On the other hand, HJA had difficulty integrating objects together. So the problem was not coming up with form, it was integrating multiple forms. So now we're going to finish up by talking about face perception and whether it's special. So one of the things that we know is that for whatever reason, face recognition is different from object recognition. So we've largely talked about object recognition as a bottom-up process. We're processing local features before we process the global features. And that's not to say that top-down processing doesn't get involved. It does. But by and large, we're going to process local over global. But face recognition is different. Face recognition involves a lot of holistic processing. So we process the face as a whole rather than breaking it down into its smaller component parts. So what do I mean by holistic processing? I mean that we are integrating information from the entire object. We're not just saying, okay, here's one eye, here's the nose and the mouth, and we're going to combine those and get the face. We're looking at the entire face as a whole. Which means instead of focusing on the individual features, we're looking at the relationship between those features. Everybody has eyes, nose, and a mouth. What makes each face different are the relationships between those different features. So another thing that makes faces special is that these features are processed in parallel, and that makes face processing much more rapid. Now, what other pieces of evidence do we have that faces are special? Well, one of the things you can do with me right now is look at this picture of Margaret Thatcher with me. And, oh, I reversed it. So you can clearly see in this instance that there is something wrong with Margaret Thatcher's face. But notice what happens if I turn it upside down. The differences are a lot less noticeable. See, this is what happens when you record it once and it fails. I forgot to flip that around. But you can see that there aren't really, it's harder to notice the differences here until you turn it around. And then it's glaringly obvious that those faces are really different from each other. So this is what is referred to as the Thatcher effect or the face inversion effect. It is harder for us to notice differences in faces or problems with faces when they are upside down. And this does not happen with other types of objects. Now, what other pieces of evidence do we have for faces being special and us processing faces holistically? Well, first we have something called the part-whole effect. This is basically the finding that it's easier for us to identify somebody's eyes or nose or lips, their features, if they are presented in a whole face rather than if they are presented in isolation. So it's easier for us to identify a feature if it's presented in a face rather than if it's presented on its own. Another piece of evidence that we have that we process faces holistically is something called the composite face illusion. So every single one of these faces probably look different to you. They look like different faces. What's actually kind of amazing here is that each of these different faces is made with the same top half. But once we give each face a different lower half, it actually changes our experience of the face. So here are all of the faces with the same top half and lower half, but you can kind of see that each of those faces looks different as soon as we give them a different bottom half. All of a sudden, each face holistically has a very different quality to it, despite the fact that all of the top halves are exactly the same. So our face is special. One other piece of evidence that we have for faces being special come from people that have prosopagnosia. That is a disorder usually due to something like brain damage or autism or things like that, where people can't recognize faces on the basis of sight. So it's a special form of agnosia that is restricted only to faces. Now, there are some things to keep in mind with prosopagnosia. Because prosopagnosia is often due to brain damage, lesions typically are not clean. They can damage a lot of other areas that communicate with visual areas that are critical for face processing. So we could have some individual differences. Additionally, the prosopagnosia that comes from brain damage might look a little bit different from the prosopagnosia that comes from something like autism spectrum disorder. And then finally, I want to raise the notion of a special face processing area in the brain. That area is known as the fusiform gyrus, to be more specific, the lateral fusiform gyrus. It is also known as the fusiform face area, or FFA. And we do find that for a lot of people with prosopagnosia, this area of the brain is damaged. Additionally, if you put people in an fMRI scanner and you look at brain activity while they look at objects, we do find that activation in the fusiform gyrus is often 2 times larger for faces than for other types of objects. But is the fusiform gyrus specifically a face processing area? Well, it does seem to be important, but it's not the only area that processes faces. Areas in the occipital lobe and the temporal lobe process faces as well. Researchers have also found that the fusiform gyrus may be selective for animals as well as faces. And some people have even suggested that it is because of our expertise with faces that the fusiform gyrus is activated. That it's an expertise area rather than a face area. So are we just face viewing experts? Is the fusiform gyrus a face viewing area? So people who believe this believe that holistic processing would occur for any category that we have expertise in. As a result, the fusiform gyrus would be activated not just for faces, but anything in our area of expertise. Likewise, if you have prosopagnosia and have damage to the fusiform gyrus, it would follow that you will also have recognition problems in your area of expertise. So let's hit each of these issues one by one. So I want to go back to those greebles. So it's possible that with more experience to greebles, your fusiform gyrus will show more activation. We do actually find that with training, participants do better at identifying greebles. However, other studies show that even with training and expertise, you do not see the inversion effect like you do with faces, and you don't get the part-whole effect, even with training, even with expertise. So here's one point for faces being special. What about the fusiform gyrus? What role does it play in expertise? Gauthier and colleagues did find that the fusiform gyrus is activated when greebles are recognized, especially if you are well trained to recognize greebles. Gauthier and colleagues also found that there is activation and expertise with faces, familiar objects, birds, or cars will actually influence activation in the fusiform gyrus. But not everybody has found this. Some people have reported that fusiform gyrus activation is no greater for untrained objects. And then let's focus on people with prosopagnosia. If that area is damaged, your areas of expertise will also become damaged if the fusiform gyrus is an expertise area. And it turns out that results don't fit with this. So Sargent and Signoret back in 1992 reported a patient, RM, who was an expert in cars and had prosopagnosia. And they reported that the patient had very poor face recognition because it's prosopagnosia, but when it came to identifying cars, the patient was still better than controls at identifying them, indicating that expertise was not damaged. So what does all of this mean? It means that expertise theory is not reliably supported. Maybe there is something special about faces, but I want to take a quick devil's advocate view. Expertise is believed to develop after 10 years or 10,000 hours of exposure, whichever comes first. You and I have gotten much exposure to faces in our lifetime due to being surrounded by other humans. Is it possible that if we could train an area of expertise to the level that we train faces, would we get the same effect? Hard to say. But ultimately, I think it's up to you, and I am going to have a test question that asks you to focus on this. So it's kind of interesting. When you go through this the second time around, I'm actually a lot faster at it. So hopefully this records. I have audio. If it doesn't, well, I'll just have to figure that out. But either way, we're going to talk about acting on objects, using our visual perception to interact with objects, and visual attention. We'll talk about that next time. Bye.